Second speaker today is Yang Fei from Nanjing University, and he will talk about rational maps with smooth degenerate Herman rings. So please.
Okay, thank you. First, I would like to thank the organizers for giving me this opportunity to give this talk. Today, I'll talk about the rational maps with smooth degenerate Herman rings. We know Herman rings appeared very early in 1970s, but the degenerate Herman rings was known only recently, and then the smooth degenerate Herman rings was very hard to find. Okay. We consider the discrete dynamic systems defined from the Riemann sphere to itself. So we consider the rational maps today, and the Fadou set is defined as the set of Z such that the sequence of iteration of F is equicontinuous at Z. And the junior set is the complement of the Fadou set. From the definition, the Fadou set is open and the junior set is closed. And each connected component of Fadou set and the junior set is called the Fadou component and the junior component. Let's sum junior sets of rational maps, and now drawing black and the white parts are Fadou set. A famous theorem of Sullivan states that all the Fadou components of rational maps are eventually periodic. If a Fadou component is periodic, then it can be defined. It belongs to one of 5 types, including super attracting Bayesian, parabolic Bayesian, Siegel disk, and Herman ring. And today we talk about the last 2 types of periodic Fadou components. And from Mitsu's result in 1980s, Herman rings and the Siegel disks can be transformed to each other by quasiconformal surgery. Let's recall some definitions. Suppose alpha is an irrational number. F is a nonlinear holomorphic gene, and the F is equals to e2 pi I alpha z plus the higher order 10. And the maximal region in which F is conjugated to the rigid rotation R alpha is a simply connected domain delta F for the Siegel disk of F centered at the 0. That means this non-linearly holomorphic gene can be non-linearizable. Then the maximal region such that the nearizable host is called the Siegel disk. The existence of Siegel disk depends on the arithmetic property of an irrational number. If we consider the continued fraction expansion of alpha, then there is a unique sequence A1, A2, and AN corresponding to alpha. And each AN is a positive integer. And the nth convergent Pn over Qn tends to alpha exponentially fast. Here Pn and Qn are cooperating positive integers. There are three important theorems about the Siegel disk. First, in 1940s, Siegel proved that every holomorphic gene is locally nearizable at the origin if alpha is the Defanti number, and then there is an index kappa corresponding to each Defanto number. In particular, if kappa is equal to 2, then this kind of irrational number are called bounded type. That means the integers of the continued fractional expression has an up bound. And then later in 1960s, Bruno generalized the Siegel's result, and he proved that if the irrational number alpha belongs to Bruno type, then this non-area holomorphic gene can be locally nearizable. Note that the Defanti numbers must be a Bruno number, and in 1980s, your course proved that the Bruno's condition is optimal. He proved that if the quadratical polynomial, if it is locally nearizable at the 0, then the rotation number of the Siegel disk must belongs to Bruno type. But this result is not known to general rational maps. This is a Siegel disk of a quadratic polynomial. When where the alpha is chosen as the golden mean, and this irrational number is of bounded type. Now we also state three big theorems of about the Herman rings. In 1960s, Arnold proved that if an analytic cycle deformation, if it has a rotation number in Defanto belongs to Defanto number, and this map is very close to a rigid rotation. That means the second condition. If it is very close to the rigid rotation, and it is univariant in a neighborhood of the unit cycle, then the map is conformally conjugated to the rigid rotation in a smaller neighborhood. So actually, from Arnold's result, one can obtain a Herman ring at that time. But in 1970s, Herman generalized Arnold's result. He don't need this the second condition. He don't need to require the map is close to the rigid rotation, and he proved the for larger set of relational numbers, the analytic cycle deformation is also analytic conjugated to the rigid rotation. So from that time, he also constructed an example such that it has a Herman ring. And nowadays we call the Herman ring as a Herman ring or Arnold Herman ring. And later your course proved that Herman's result is also optimal in the sense that if the rotation number is not in Herman's class H, then he can find an analytic cycle deformation such that it has a rotation number of alpha, which is not analytic nearizable. So in some sense, for Siegel disk, the Bernoulli type is optimal for the maps to nearizable. And for Herman rings, the Herman numbers are optimal to nearizable. This is a Herman ring of a cubic rational map. It is a cubic Blaski product and has a rotational number, the golden mean. But here, t is not equal to number. T is an irrational number such that this map has a rotational number rho f on this cycle. And Mitsu has proved that Herman rings can be constructed from Siegel disks. From Herman's Arnold and Herman's result, people can only construct the Herman rings of periodic 1, and the Herman rings are symmetric about the units about the cycle. But from Mitsu's construction, people can construct Herman rings of any periodic, and also can construct the Herman rings which are not symmetric. And this is a kind of a quasi-conformal surgery. If you have a cycle of a Siegel disk here, and then you paste a cycle of a Siegel disk along the center of these disks, like this. Then you obtain a sphere containing a cycle of annulus. Then you can find a invariant complex structure on this sphere. Then you obtain a rational map here, and then you obtain a cycle of Herman rings. This is the classical Siegel-to-Herman surgery. We will also use this surgery today, but we will work on a periodical 1, and we also but because we need to construct the long symmetric Herman rings, so Arnold and Herman's method cannot work here. Let's back to our title of this talk. In 1920s, Badu stated in his paper that he was going to study the invariant analytic curves of rational maps. But as far as we know, he never come back to this topic. One of the motivation to study the invariant analytic curves is to the composite dynamics. So if a rational map has dynamics on the Riemann sphere, but if we can find an invariant set, like invariant analytic curves, so we can restrict the dynamics on some subset of the Riemann sphere. For this topic, there are some progress. For rational maps, the invariant analytic curves are allowing as cycles. That means spheric cycles, level curves of nearization functions of Siegel disk and Herman rings. We know in the Siegel disk and Herman rings there are many invariant curves, and these curves are all analytic. In 1980s, Avila proved that if f is an n-type function, anti-function, including polynomials and transcendental anti-functions. If this map has Jordan analytic curve, Jordan analytic means it's analytic curve, but it is simple, it's a Jordan curve. Then either gamma is a circle and f is conformally conjugate to g to the n, or gamma is a level curve of the linearization function of some Siegel disk. And in 2012, Eremenko shows that there are Jordan analytic curves, like including algebraic and non-algebraic curves, which are not circles and invariant. And moreover, the restriction on each of these curves is not a homomorphism. So in this case, the junior sets are the whole Riemann sphere, and the Eremenko find many algebraic and non-algebraic Jordan analytic curves, and the restriction of these maps on the curves are not homomorphism. If we allow the curves to have some degree of smooth, then there are many invariant curves. For example, if we have a parabolic basin with only one petal, then the left curves of attracting Fadou coordinates is C1 smooth, like the blue curves and the green, the red curves in showing on this picture. And for Siegel disk, Prismarco and Avila Buff Chéritat construct many C-infinity smooth boundaries of Siegel disk. Their idea is to make a perturbation of Siegel disk. Suppose if you have a Siegel disk here, this Siegel disk is a quasi-circle containing a critical point and boundary. So this curve is not smooth at any place. But if you perturbate like this, if you have an alpha 0 here, then you take an alpha 1, which is very close to alpha 0, then the boundary of a Siegel disk will oscillate like this. Then you have an alpha 2 corresponding a Siegel disk oscillating more and more, and then like this. And you can see a shape here. This is not the boundary of the Siegel disk, but you can imagine at the limit, this curve, a very curve close to this curve will become the boundary of a Siegel disk. That will be smooth. If we take a limit of alpha n, you obtain an alpha prime, then the Siegel disk corresponding to alpha prime will have a bound of a Siegel disk whose boundary is smooth. And use some kind of this method. Buff and Chéritat proved that there are Siegel disk of Cn, but not Cn plus 1. And also there exists Siegel disk C0, but not Horde continuous. And then they can also use the similar argument to produce the Herman rings with boundary C infinity smooth. Let's give the definition of a degenerate Herman ring. What is the degenerate Herman ring? It is a Jordan curve, and it is not a spherical circle, and satisfies the following 3 properties. The first one is this Jordan curve is contained in the junior set of the rational map, and this curve is not a boundary component of any Siegel disk or Herman rings. So we don't consider the boundary of rotational domains. And the third property is it is invariant and conjugate to an irrational rotation. Note there is a circle here. This is a unit circle. This is the unit circle for the this unit circle which is invariant under the Blaski product when A equals to 3. And this is unit circle. You can see it satisfies all these three properties. This unit circle is not contained in the junior set, and then this is not the boundary of any single disk or Herman ring. And you can choose suitable T such that the map is conjugate to an irrational rotation. But if we require it is not a spherical circle, then this circle is not a degenerate Herman ring. But in some things, in this case, this curve can be seen as a degenerate of the left picture. The left picture has a true Herman ring here. It has the positive modulus containing the unit circle when A equals to 4. If the number A decrease from 4 to 3, then this ring will become thinner and thinner, and then the limit is this picture. So you can see degenerate Herman ring sometimes comes from the true Herman ring when the modulus tends to 0. But in this procedure, you need to grant that the rotation number is equals to a fixed number. Here we choose the rotation number to be the golden mean. So if you want to construct a degenerate Herman ring, actually it's not very hard. You can use quasiconformal surgery to destroy the symmetrical property of the Blaski product. The left picture is the schedule picture of this map. This map is a Blaski product. You have a unit circle, suppose a unit circle such that this map satisfies the three properties on this unit circle. If you destroy the symmetric such that you let the multiplier at the origin to become a lambda, the lambda modulus of lambda between 0 and 1, then you can obtain a rational map which is quasi-symmetrically conjugate to the left map in their corresponding neighborhood of junior sets. And for this map, you also have the invariant curve here. But this curve is not this curve is the quasi-conformal image of the unit circle. So this curve is a quasi-circle. This quasi-circle is a degenerate Herman ring. Is a degenerate Herman ring because it cannot be a circle. Otherwise, this map must be a Blaski product. So this map is not a circle, and the restriction of this map on this circle satisfies the three properties mentioned just now. And this is degenerate Herman ring constructed by quasi-conformal deformation. And in some sense, this construction is somewhat trivial, but based on the quasi-conformal surgery. So Eremenko asked the question: does there exist C infinity smooth degenerate Herman ring? So he required the degenerate Herman rings to be C-infinity smooth. In this surgery, quasiconformal surgery, this circle only is only a quasi-circle. You cannot guarantee this circle is C-infinity smooth. So we need to find other methods to construct such kind of degenerate Herman ring. And our main result is such kind of Herman ring, degenerate Herman ring exists indeed. We can find such maps in cubic rational maps. And the main ingredient in the proof includes 4 parts. The first one is we use Mitsu's classical Siegel-to-Herman quasi-conformal surgery. The second is Avila Buff Chérita's construction of smooth Siegel disks. And the third one is we need to control we need to use Buff and Chéritat's result to control the loss of the back measure of quadratic view in junior cells. And the fourth property we need to use is the rigidity of the cubic maps having boundary type Herman rings. The general idea is we cannot construct the degenerate Herman rings directly, but we can use the surgery to transfer the Siegel disks to Herman rings. So we can obtain a family of cubic rational maps and try to disturb the Siegel disk. When you disturb the Siegel disk, then you will obtain a family of Herman rings. And we need to prove the limit of the Herman rings is a degenerate Herman rings. So when we take in limit, we need to prove the sequence is convergent. And in this procedure, we need to prove a family of quasi-regular map and the corresponding quasi-conformal mappings are convergent. In this process, we need to control the loss of area of quadratic field in junior cells. And then we need finally use the rigidity to show the limit map is what we want. Let's work this proof in detail. Suppose alpha is an irrational number and the Pn over Qn is the nth convergent of alpha. If alpha is regional, then the quadratic polynomial has a Siegel disk delta alpha centered at the origin. And then there exists a unique positive number R alpha such that and a conformal map phi alpha defined from the disk with radius R alpha to the Siegel disk delta alpha with this normalized the condition phi alpha fixed at 0 and the derivative of phi alpha at 0 is 1. This map conjugate the rigid rotation to the P alpha in the Siegel disk. When this map is normalized, then when this near region map is normalized, then this R alpha is unique. And this number R alpha is called the conformal radius of delta alpha. This is conformal radius. And to construct a Herman ring from a Siegel disk, we use the classical surgery, and we can see the P alpha here. P alpha is quadratic polynomial, And we also consider P minus alpha, and we paste the outside of this invariant curve of P minus alpha at this place to obtain a quasi-regular map big F alpha. And if we want to construct the degenerate Herman rings, finally, we need to choose grant that the two critical points here and here are not symmetric. So we put a critical point here and put a critical point here. They are not symmetric about the circle. And in this case, when we take a limit, then the resulting map is not is not a plastic product. So we will orbit a degenerate Herman ring. And at the beginning, these maps, these alpha are all of bounded type. So the boundary is a quasi-circle and containing a critical point. You know, for P alpha, you have a conformal regulus R alpha, and for any R between 0 and R alpha, you can make a surgery such the resulting map has a Herman ring with modulus with a modulus which can be calculated precisely, and you can see in the quasi-conformal coordinate of F alpha, the Herman ring were corresponding to this annulus, and in the quasi-conformal coordinate, it will have it is conformally equivalent to this annulus. This annulus has outer boundary of this disk and the inter boundary of this and boundary of this disk. And from this classical surgery, we know if you give any alpha Bruno type, actually you can choose it to be a bounded type is sufficient for our proof. But this result is proved for Bruno type. And then you can find a quasi-conformal surgery phi alpha. This is the quasi-conformal map. Gives with some normalization conditions such that the phi alpha conjugate the quasi-regular map to a cubic rational map Q alpha. This is cubic rational map. It has 4 critical points. After this normalization, it has 4 critical points at the 0, 1, infinity, and C. And this C depends only on A. And it has a fixed Herman ring A alpha with rotation number alpha, which is the same as P alpha. And the modulus, the conformal modulus, this number from the construction. Like here is this is the annulus in conformal coordinate corresponding to Q alpha. Okay, we also proved that the junior set of Q alpha has area 0 is equivalent to the junior set of the quadratic polynomial P alpha has area 0. And if alpha is bounded type, then each boundary of the Herman ring is a Jordan curve passing through exactly 1 critical point. And the area of junior set has is 0. And we also need to the rigidity of the maps. That means if you give three numbers, the first one is the rotation number of bounded type, rotation number, and R between 0 to the R alpha. R alpha is the conformal radius. And you also give a number theta between 1 and 2 pi. Then you can find a unique A. A is the parameter, and a unique U depending on alpha R theta. So this Q corresponding to this cubic rational map QAU. This map is unique determined by these three numbers, alpha, R, and theta, such that it has a Herman ring satisfying the following condition, the following properties. The first one is Q alpha has the restriction of Q alpha, QAU on Herman ring has rotation number alpha, and the modulus can be calculated like this. And the boundary, the outer boundary of the Herman ring and the interior boundary of Herman ring passing through two critical points 1 and C respectively. And the conformal angle between 1 and C is theta. That means if you give three numbers alpha, R, theta, then you can determine a unique map QAU such that it has a Herman ring satisfying some geometric properties. It has a rotation number alpha. It has its conformal modulus can be calculated like this, and its boundary contains two corresponding critical points, and the conformal angle is theta. Conformal angle you can see in this picture. You can image this point. This critical point is 1, and this point is C. And the conformal angle, that means in the you have an angle here and you have an angle here. Then the angle between these two segments is the conformal angle. That means the angle of two critical points in the conformal coordinate. Okay, now we need to study the Sage's continuity. If you give these three numbers, alpha, R, and theta, then there exists a conformal map chi alpha R theta, which maps the annulus, the round annulus to Herman ring. Oh, just at this place, we need to mention that you know, this is the formula of this. This is the formula of this rational map QAU, and it can be also written as Q alpha R theta. So sometimes we use Q alpha R theta, sometimes we use QAU. When you look at the Q alpha R theta, you know some properties very well. But when you look at QAU, sometimes you don't know the properties. But this kind of map you can write is a formula like this. But from this formula, you sometimes you don't know this information. So from this result, we use these two kind of notations. Interchange use these two kind of notations. And if you give these three numbers, there exists a conformal map defined from the annulus, round annulus to the Herman ring. Actually, this map is the nearization map. And for the proof, to study the continuity of the surgery, we need to control the Baytrim coefficients. Baytrim coefficients. So we need to study the measure of some sets. To control the Bayes measure, we need to follow the Buff and Chéritat's result on the controlling of the built-in junior sets or quadratic polynomials. But the proof but the layer proof relies on Eno-Shishikura's linear parabolic renormalization. To apply this theorem, they need to require the rotation number in high type numbers. That means the digitals A1, A2, and AN are all larger than fixed number big N. So in following, we need to require the numbers are in high type and alpha is given in bounded type but high type. Then one can apply the near parabolic renormalization, and then one can control the Bayes measure of built-in quadratic junior sets. For the continuity of the surgery, we need to use this lemma. For given alpha in bounded type and the high type number, and the number R and alpha 0 and between 0 and alpha and the theta between 1 to 2 pi, we define a sequence of alpha n like this: A1, A2, AN, and big AN and the big N, with AN equals to this number R alpha over alpha 0 QN. Note that when n is large enough, then this number is also bigger than big N. For if we choose alpha n like this, then we can show that alpha n tends to alpha. This can be verified very easily. And alpha n tends to alpha 0. This is a result of Avila, Buff, and Chéritat, this place. If you choose alpha n like this, then the conformal radius also has a limit. This limit is alpha 0. Note that the limit tends to alpha, but the conformal radius does not tends to R alpha, but tends to alpha 0. You can see like this, because you choose AN like this. There is alpha over alpha 0. And we can also prove the corresponding rational map has a limit. To show this host, we need to consider this sequence Q alpha N alpha theta. It is a conjugate of big F alpha N like this. You see these three maps F alpha N. When you can show it converges to F alpha by the surgery construction. But if you want to show the convergence of this quasi-conformal map phi alpha N, then you need to use the Buff and the Chéritat's result to control the Bayes measure of the built-in junior sets of quadratic polynomials to control the Bayes differentials, and then to show the convergence of this map. And if you show the convergence of these maps, then you can show the convergence of these rational maps. So you can also show the there is a sequence of near-region map chi alpha and alpha theta such that it is convergent to the limit chi alpha r theta. And there is also a small circle property. If you give any epsilon, if n is large, then the Q alpha and r theta has two repelling circles, which are very close to these two caps. And these caps, you can see these two caps are contained in the Herman ring of Q alpha r theta. And for the small circles, the result is based on the Avila Buff Chéritat result. There is a picture. You begin Q alpha r theta like this. This is the this is the boundary of a Herman ring of Q alpha r theta. Then you make then you find alpha n tending to alpha. This is alpha 1, this is alpha 2, this is alpha 3. And you can see if you take in limit, and you will find that the Herman ring, the conformal modulus of Herman ring will become small and small, and there are some small some repelling circles close to the boundary. So this is the first step. When you have a p alpha p minus alpha to orbit in q alpha, if you take a limit, if you use quasi-conformal surgery and then take a limit, you orbit q alpha n based on p alpha n and the p minus alpha n. From the Mayer's lemma, we can see this sequence is convergent. So this is the first step. And the second step is if you want to construct a degenerate Herman ring, then you can do like this. From this picture, you obtain this picture. And then based on this picture, you can also find another irrational number such that you have a cubic rational map. Its Herman ring is more closer and closer. And based on that, you can obtain another rational map, and such that the modulus of Herman ring would tending to 0. The limit set is a degenerate Herman ring. You have inferent cap here, and then if you take a irrational number which is very close to the original irrational number, you can grant that there is some inferent cap which is very close to the first cap, and the limit is a degenerate Herman ring because you can find the repelling circles approaching to this cap from both sides. So you can show the limit is not contained in the boundary of Siegel disk or boundary of Herman rings. Then this is the theorem. If you give a boundary type and a high type number, and you choose R between these two numbers, and then this is the beginning cap GT. This is the cap here, like here is here, and then you can finally find the alpha prime such that the QA prime U prime it has a degenerate C infinity Herman ring, because in each step you can control the regularity of this cap. You have a C smooth cap here, and then you can also have a C smooth cap here. You have C infinity smooth cap here, and the limit is also a C infinity cap. You can do this in the ratchet space. Okay, this is the first result, and now I will spend only 2 or 3 minutes to state the second result. The second result is about the area of the junior set. To study the area of a junior set, it dates back to Fadu in 1999. And he studied the Lebesgue measure of the contour junior sets and proved that the contour junior sets has a Lebesgue measure 0. For the Lebesgue measure of no well-dense junior sets of rational maps, there are many fruitful results, especially about the zero area. It studied by Doadi, Hubbard, Nebich, and Mitsu, and some others. But for positive area, now there are 3 big results. Buff and Chéritat, he proved that there existence Siegel-Cream or invented set-net renormalization or unbounded completorics quadratic polynomials having junior sets of positive area. And Avila, Nebich, Dudko, Nebich, they construct other 2 types of infinity renormalization quadratic polynomials having junior sets of positive area. And note that these maps either have irrational periodic points or are infinity renormalizable. And our result is we can construct cubic rational maps having a low well-dense junior sets of positive area, for which these maps has no Siegel disks, no Herman rings, and are not renormalizable, and also no Herman rings. Because if you have example like this, you can construct some maps has no Siegel disk, no cream points, not renormalizable, but having Herman rings with positive arrow. But we can produce the maps which belongs to any which does not belong to any types of any of these types. Actually, our result is the cubic rational maps having degenerate Herman rings. Intuitively, it produced the pasting 2 quadratic Siegel disk along their Siegel disk boundaries. So this kind of maps has no Herman rings, no Siegel disk, no cream points, and are not renormalizable. But this result is a byproduct of this result. In the proof of this result, to construct the smooth degenerate Herman rings, we can also obtain this result at the same time. We also would like to mention that recently Lim gives another method of constructing non-trivial degenerate Herman rings. That means not by quasiconformal deformation of plastic products, then based on study prior bonds of bounded type Herman rings. And the degenerate Herman rings constructed by Lim are quasi-cycles passing through critical points. His degenerate Herman rings are considering to net the conformal modulus of Herman rings tends to 0 and consider the limit. And he shows the limit has a degenerate Herman ring and containing the critical points. Because this degenerate Herman rings contains critical points, so they are not smooth. Actually, Eremenko asked a question, does there exist a Jordan analytic invariant curve of a rational map different from a cycle which is mapped onto itself homomorphically and intersect the junior set? Note that Eremenko can construct this kind of curves for latex map, but the latex maps the curves to self not homomorphically. So he asked, does there exist such kind of curves such that the maps these curves homomorphically, but this curve must intersect the junior set. So a later question is, does there exist analytic degenerate Herman rings? Not that we constructed the C-infinity degenerate Herman rings. Does there exist analytic degenerate Herman rings? We don't know because the method in this talk does not give a conclusion of this result. Finally, I would like to raise two questions. The first one is, does there exist a smooth degenerate Herman rings whose rotation number is not of Bernoulli type? Because our quasi-conformal surgery, from our quasi-conformal surgery, we can the examples we constructed are all degenerate Herman rings with rotation number of Bernoulli type. So if the rotation number is required to non-Bernoulli type, we don't know how to produce such kind of examples. Because if not the Bernoulli type, then we can't have a single disk fast. Then we can't use quasi-conformal surgery. The second question is, does there exist a degenerate Herman ring which is not a quasi-cycle? Because our construction generate the Herman rings, the C infinity degenerate Herman rings, and the names result also produce some degenerate Herman rings are quasi-cycles. So our results produce Herman rings, degenerate Herman rings are quasi-cycles. So a question is, does there exist a degenerate Herman ring which is not a quasi-cycle? So I think I need to stop here. Thank you very much.
Yeah, thanks a lot for your interesting talk. Yeah, so let's thank our speaker here. And let me start the discussion. So are there comments or questions? Yeah, Mitsu.
Hi, Yonfei. Thank you for the talk. So when you prove that the circle is smooth, so do you show that the conjugacy from a rigid rotation actually converge in the smooth topology?
Yes.
Okay. But so the conjugacy, the domain of definition for the conjugacy shrinks to the circle, not in the neighborhood of the circle. Is that correct?
I think I think I don't need to show the conjugacy map. Yes. I need to show I need to show the convergence of the conjugate map phi. You mean phi n or? You mean
what was it? Phi n was a QC conjugacy between.
QC conjugacy. Yes.
And so how did you show that the conjugacy actually converges in a smooth topology?
Actually, I don't need to show the convergence of the quasi-conformal map phi n. And actually, there are two steps. The first step is to show the first step is to show the convergence of the quasi-conformal map. But at this step, there is a neighborhood of the smooth curve in the center of the Herman ring at the first step. At the first step, I don't need to show the convergence of quasi-conformal map in smooth topology. In first step, I don't need to show this property. And in the second step, when you need to show the convergence of the maps, the caps, because these caps are smooth caps in the center of a Herman ring, and you can control the smoothness at each step. You can control the convergent at each state. And at each state, you will have a neighborhood around the invariant caps.
So somehow you have a control on the geometry for the invariant curve and in order to show the smoothness of the curve, the limit?
I can just to show it. It's C infinity smooth. I do because you begin with a C smooth curve, and then you use C smooth curve to approximate at each step, and then finally you also get a C smooth curve like this. The limit curve is also C infinity smooth.
Well, maybe
Actually, at each state, these curves are analytic curves.
Yes. But the limit, you have to show somehow that it is smooth.
Yes,
Well, the limit is always analytic, but
the limit is we cannot say the limit is analytic, but the limit we can say it is C infinity smooth, just in the C infinity topology. Yes.
Okay. Maybe I give other people time to ask you questions.
Yeah. So are there other comments or questions?
Can I ask another question?
Sure.
So you showed this trivial case starting from a symmetric Blaschke product, and then maybe you do the surgery or something to create the quasi-circle, which is invariant.
Yes.
The trivial case you mentioned. So in that case, do you know for sure that the curve is not smooth? Or
no, I don't know. Maybe no, I'm not sure. I just say I cannot. The surgery cannot grant the smoothness of the curve, but I don't know it is smooth or not. I don't know.
Okay.
Maybe it is smooth.
Okay. Thank you.
Thank you.